Okay, good evening, everybody. My name is Paul Ceruzzi. I'm the chairman of the Space History Division here at the National Air and Space Museum. And I want to welcome you to the third installment of the 2012 Exploring Space Lecture Series. And I hope you, those of you who've come early, I hope you've been enjoying the various activities that we've had, not just here, but also out in the floor of the museum. And perhaps you had some encounter with our education people who are demonstrating black holes, which is kind of cool, and really appreciate their contribution to these events. Yes, really, we really do appreciate it. So definitely, and we also want to thank our sponsors, as they have for the past 9 years. The Science Mission Directorate of NASA continues to be a great friend in supporting this series. And tonight, NASA is represented by John Grunsfeld, Associate Administrator for the Science Mission Directorate. And I think that's a name that's probably familiar to many of you. If you know anything about the servicing missions of the Hubble Space Telescope, you know the name of John Grunsfeld. And we also want to welcome back Michael O'Hara of the Aerojet Corporation, which has joined NASA for the 2012 season. So why don't you just stand up very briefly, John and Michael. There you go. Yes, thank you very much. Okay, tonight's speaker is Dr. Neil Gehrels, Chief of the Astroparticle Physics Laboratory at the NASA Goddard Space Flight Center. Dr. Gehrels is well known as an experimental physicist and a leader in gamma-ray astronomy. He's studied gamma-ray bursts and supernovae and is presently principal investigator for the SWIFT gamma-ray burst mission. He's held many positions at NASA, including project scientist for the Compton Observatory from 1991 to 2000. He's held posts of the chair of the American Astronomical Society's High Energy Astrophysics Division, chair of the American Physical Society's Division of Astrophysics, a member of the American Academy of Arts and Sciences and the National Academy of Sciences. Now, to share a few things, thoughts about Dr. Gehrels, though, I want to first introduce John Grunsfeld, who will say a few remarks, and then introduce our speaker tonight. So take it away, John.
Thank you very much. It was fun to hear Neil talking a little bit informally before the start of our formal activities tonight, and it's really a pleasure to represent the National Aeronautics and Space Administration here tonight. And I'm just thrilled to see all of you coming out to learn something about the nature of our cosmos. I, as you heard, took a little bit of risk going up in the space shuttle to try and enable great science, and I like to say to help unlock the mysteries of the universe. And Neil has made his career doing that. For the young man who asked about heroes in science, I can't help. I wanted to answer, and we all have our own answers. But my hero in science was Enrico Fermi, who is an American physicist, first person to develop or with a team, first atomic pile. But before that, he was a cosmic ray physicist. I went into cosmic ray physics, worked on all kinds of cosmic questions, put thought into extraterrestrial life, which is something I'm very interested in, the question of are we alone in the universe. But he was also a great mountaineer. He liked to go out and have great adventures. And we recently named a satellite after Enrico Fermi, the Fermi Observatory, something Neil has worked on. Neil is, as you heard, chief of the Astroparticle Physics Laboratory at the Goddard Space Flight Center, has had a very long and distinguished career in high-energy astrophysics. He and I both have an interest in doing imaging and hard X-rays and gamma rays. In fact, he and I worked on the Compton Observatory together as young researchers. I worked on the burst and transient source experiment, looking at gamma ray bursts, which will be a topic tonight. He was working at much higher energy, something I was interested in. Betsy was not an imaging detector. Egret was an imaging detector. And we also share a little bit of educational background. I was a postdoc at a small technical school on the West Coast called the California Institute of Technology. A few years earlier, working with the same advisor, Ed Stone. Neil was a PhD student. That's where he got his doctorate from Caltech. He's received many awards, and I don't want to go into all of them, but one in particular, the Bruno Rossi Award, the Rossi Award of the American Astronomical Society, which is a very prestigious award for somebody in high-energy astrophysics, well-deserved, and also the National Exceptional Scientific Achievement Award, or medal. But there's a different side of Neil that I've learned to appreciate, but it's very consistent with his scientific curiosity and his love of exploring science. And if you can bring up the slide, that's Neil on your right, that's me on the left, at 19,000 feet on the flanks of a mountain called Aconcagua, the highest mountain in this hemisphere. And there's a large glacier behind us, and we're trying to keep warm. He has an ice axe in his hand. And, many people would say that, this is sort of an adverse environment, but, Neil has a high tolerance for adversity and, in fact, enjoys being in tough conditions. He was my tent mate for our 2 weeks on the mountain there. And, being in the mountains, trying to achieve hard things, the question about what do you tell your science students when they say, hey, this is hard. And one of the answers is that when you strive for something that's hard and you achieve it, that's the best satisfaction you can possibly get. But also, I hope you appreciate this, maybe you will, maybe you're not, it's also the most fun. And I think I can speak for Neil, I know I can speak for Neil in saying, one of the reasons Neil has been so successful is because he finds the science, compelling, engaging, and fun. It's so personally rewarding that it gives you that great sense of pleasure, that others would find, perhaps playing softball or other endeavors. And believe it or not, mountaineering, living in freezing cold conditions and no showers for weeks and eating freeze-dried food and all the rest is also a lot of fun. Sometimes it's more fun afterwards thinking back on it, but it's also a lot of fun. Somebody asked about funding. My job now is to make sure brilliant people like Neil have good funding, and I take that very seriously. And we do have very strong bipartisan support for the funding for NASA, for the science we do. In the 50 years of NASA's history, science has provided the real backbone, the great consistent interest through our missions, through missions like the Compton Observatory, the Hubble Space Telescope. Somebody asked about archival research. Half of the scientific results that come out of Hubble now come from data in the archive. And I think that'll be true for SWIFT and all the other missions. Now, you all came here to the National Air and Space Museum, and I, again, thank you for coming out. You didn't pay an admission coming in, but unfortunately, again, we talked about funding. I have to break the news to you that actually tonight's event is not free. And you're thinking, oh yeah, he's going to say we paid taxes and things like that, and you do, and I appreciate that, and it allows us to fund the great research. But actually, there's a specific tax for all of you tonight, and it's more your homework assignment. You've come out here to learn something tonight, and again, I think that's just terrific. I'm excited that we're not looking at a bunch of empty seats, we're looking at mostly full seats. But your fee for coming here tonight, or your homework assignment, if you choose to take it, if you find Neil's talk interesting tonight, is that I want you to go out and share that knowledge that you've gained. Share it with your neighbors, with your friends, with your schoolmates, whoever you interact with over the next week or two. Is that I'd like to extract that payment from you. Is go out and share this knowledge, because what you're going to hear tonight about gamma ray bursts and black holes and the birth of black holes is a really fascinating story, and retell that story. Neil.
Thank you, John. That was a great introduction. Thank you. Okay, so I'm going to be talking about gamma ray bursts and the birth of black holes, and we're going to have some fun tonight. We're going to be talking about results from the SWIFT Observatory, which is one of these explorer observatories. At the moment, it's actually the only explorer the astronomical explorer that's flying, but John is working hard on bringing up some new ones in the near future. We've had as many as 4 at a time in orbit. We proposed SWIFT to NASA. I led an international team. I was at a NASA center, but we included universities and people in the UK and Italy. We proposed this as a mission, and it was one of 40 that went in at that round in 1998. And 2 of them were selected for study, and in the end, only one of them is on orbit. So it was very hard competition, and we were delighted that we won. We had some new technology that we were bringing forth, and I think that was a factor, and I'll show you a little bit about that. After many hard years of development, 5 years, although that isn't very long by space standards, we launched in 2004. And here's a beautiful picture of the launch. I'm going to show a movie of the launch as we get into the talk. And the science of the SWIFT observatory is to study gamma ray bursts. In a few minutes, I'll tell you what gamma rays are and what gamma ray bursts are, so don't worry if you don't understand that jargon. But just to put it in a nutshell, we're studying the biggest explosions in the universe with SWIFT that we think are caused by the birth of black holes. Mario Livio at the Space Telescope Institute calls it the birth cries of black holes. And so I thought you would be quite interested to learn about black holes. So I'm going to start this lecture by really talking about black holes, the history of black holes, the people that were involved, and what we now know and what we don't know about black holes. What is a black hole? The observational evidence we have that there are black holes, and then go into the results from SWIFT and talk about SWIFT, gamma ray bursts, the birth of black holes, and get back to in the end, and I think you'll find this really interesting and kind of philosophical, scientific question again, what is a black hole? So in the beginning there was Einstein, everything always goes back to Einstein. 1905, Annus Mirabilis, the miracle year. He had 3 major papers that year, explaining the photoelectric effect, which gave us the particle nature of light. Light can both be a wave and a particle. Brownian motion, which supported the atomic nature of matter. Suspended small particles in a liquid are bouncing around due to the atomic interactions with them. And special relativity, which says that the physics is the same in any non-accelerating frame that you're in. So if you walk down the aisle of an airplane going 600 miles an hour, you can't tell that you're in an airplane unless you look outside. It feels the same as walking on the ground, and that's special relativity. And one of the consequences of that is that the speed of light is the same in all frames. And another outcome of that is the famous law E equals mc squared. Well, 1907, Einstein had what he called the happiest thought of his life. Okay, so it was something profound for Einstein to be happy. And here's what his thought was. This is eventually leading to his general relativity theory. His thought was, if you're in an elevator and you're accelerating, it feels just the same. In fact, all the laws of physics are the same and all of the forces are the same as if you're on a gravitating planet or some gravitating object. So the force of gravity and acceleration are equivalent. And we know this all the time. If you're in an elevator and it starts going up, it feels like you're being pulled more to the ground. And it even comes into our language. Fighter pilots talk about pulling 3 Gs when they go through an acceleration and they're pushed into their seat by 3 times the force of gravity. And so, okay, so that's a happy thought, but what did it mean? And it actually took him 9 years to fully develop this theory, and that is essentially that massive objects like stars or any kind of mass cause deflections and curvature in space and time. So you can see in this nice little drawing here on the screen, you can think of a particle, let's say an asteroid going by the Earth, and gravity pulls it in, and so it deflects its course and it goes out in a different direction than it came in. But another completely mathematically equivalent way of talking about this is that the sun or the star causes a curvature of space around it. And so this asteroid comes in and it goes into this curvature, this curved well, and comes back out, and they're exactly the same. So it took 9 years for him to realize and put this all into mathematical terms, and it became the theory of general relativity. And his Einstein field equations describe this. And he developed this theory really for understanding the cosmos and cosmology. The next person that's important for the black hole story is Schwarzschild. Because Einstein hadn't thought about this in terms of stars and objects. He was thinking about the whole universe and whether it's accelerating or constant. He thought it was constant. But Carl Schwarzschild is the first person who produced the solution to Einstein's equations in an astronomical setting for a spherical star at rest. There's a pretty interesting story about Carl Schwarzschild. He was 41 years old. He was the director of the Potsdam Observatory in Germany, and this was the time of World War I. And he volunteered at this fairly late age to go fight on the Russian front, which was, a really tough assignment. And he was an artillery officer. So he was serving on the front, and he was getting some kind of messages still from the home country, and he heard about Einstein's theory of general relativity. And he sat in his tent and actually worked out this solution, the Schwarzschild equations, to solve the equations for this star at rest. And he came up with a really interesting solution. It describes the curvature of space around a star, but it has a singularity in it. Now, what does that mean? That means that the equation blows up. It has a zero in the denominator. This occurs for a very sort of bizarre case, and it wasn't appreciated at the time of his theory. If you can take a star like the mass of our sun and crunch it down into a really small size, then for the mass of our sun at a distance of 3 kilometers from this crunched down star, the equation blows up. Time becomes infinite. Space, crunches down to 0. And it wasn't understood to realize that there was a singularity. This radius was called the Schwarzschild radius. This will eventually become the event horizon of a black hole. But at that time, they had no idea that you could actually get a star into that smaller region. So it was more of a curiosity. In fact, Einstein never believed that this singularity would have any effect. He didn't even think it was real. And this Schwarzschild radius is also the distance at which light could not escape from this condensed star. Carl Schwarzschild got ill when he was on the front, and within a year after coming back to Germany, he was dead. So he did this one thing, really important thing. So then we move on to Oppenheimer, Robert Oppenheimer, the father of the atom bomb, who actually spent the rest of his life after World War II convincing the world to not use nuclear weapons again. He became a pacifist and a very effective, although he was persecuted by many people. And he, with a student, Snyder, showed that you actually could get a star, a really compact star. They didn't have any real evidence that there were such things, and they didn't know exactly how it happened. But he showed that if there was no forces and the mass of the star was large enough, there's nothing to stop it from contracting and going all the way, essentially contracting to a point source. In certain circumstances, which I'll show you in a minute, the whole star can collapse to a single point, essentially a black hole. He called it a dark star or a frozen star. The name black hole hadn't been invented. And so here I'm showing you, this is a SOHO movie of the sun. I'm not sure why it's rotating so fast, but it's a beautiful image of the sun by the SOHO satellite. Every star has nuclear burning taking place inside of it. It's nuclear fusion. And it's what produces the energy inside the star that holds it up from collapsing. So this is happening inside our star. Star starts out being mostly helium and hydrogen, and then it ends up in this onion kind of configuration, which you can see on the screen here, where the nuclear burning transforms the elements from hydrogen to helium to carbon to silicon to oxygen, and all the way to iron at the core. The whole time that this is going on, there's energy produced and it holds up the star. But when the core becomes iron, it's the most tightly bound nucleus, and there's no other burning that can create energy. And so the core grows and grows, and it's not producing any light, and eventually it becomes overwhelmed by the force of gravity. In a star like our sun, this star will collapse, and quantum mechanical effects will hold it up, becomes a white dwarf. But if it's a massive star, greater than 2 or 3 times the mass of our sun, it'll overwhelm those quantum mechanical effects and it'll actually collapse in the center. And so this is the kind of process that can produce a black hole. And since we're looking at stars, I thought of this cartoon that I really like. Again, Jones's colleagues aimed the telescope sneakily at the sun. Now, the person who came up with the name of black holes was John Archibald Wheeler. He's a famous physicist. He did many different things. And this is a picture of him actually emerging from a conference in Black Hole, Nova Scotia, which is, it actually was a pirate's cove on the Bay of Fundy with these really high tides. You may have heard of it. And he was giving a talk in 1967. In response to questions, he coined the term black holes. So maybe we could coin some new term tonight. I'm not planning on it, but you never know what'll happen. And black holes had been used before. That name had come along. It's really a negative kind of term. If you're an astronomer, you now just think about these objects. But if you listen to the vernacular, you'll hear people say, "Oh, your room is like a black hole," or even worse, "My job is a black hole." It's not good. And going way back in history, the very first usage of this name was really negative, the Black Hole of Calcutta. And it was the British East Indies trade company that was in India, and some of the rulers in India were very much opposed to them, and so there was a minor war always going on. And the Nawab of Bengal in 1756 imprisoned 146 British POWs into this tiny little cell. And you read here, "The dungeon was strongly barred room, was not intended for the confinement of more than 2 or 3 men at a time. There were only 2 windows and thick iron bars which impeded the ventilation. The prisoners were packed so tightly that the door was difficult to close. And when they opened the doors the next day, of the 146, only 23 were alive." And this is the first actual use of the word black hole. So it's kind of a squalid history. What actually is a black hole? We'll start talking a little bit about science here. So mathematically, it's a star or an object that's collapsed to a point. It's actually a mathematical singularity. It's a single point. No light can escape from this object. There's a Schwarzschild radius. For the sun, it's at 3 kilometers. It grows linear with the mass of the black hole. And it's a mathematical construct of general relativity. We now have evidence, and I'll show you in a minute, that there are black holes in the universe. But when this was first realized, especially by John Wheeler, even going back to Carl Schwarzschild, people didn't think that there really would be black holes. And John Wheeler came up with this interesting theorem, which we now believe is really true, that black holes have no hair. Now, what that means is that there are only very few properties that a black hole can have. It can't have color. You can't see oceans on it. You can't see any kind of texture. It can only have mass and spin and charge. In astrophysics, we don't usually end up with a charged object because if something's positively charged, it'll suck in negative charges and become neutral. But we do see that black holes have different masses, and we are just beginning to be able to measure their spin rate. And I'll show you some evidence here of black holes. When John and I were students and in the 1970s, there was an object in the universe that everybody sort of talked about as a candidate black hole. We had no strong evidence that it was a black hole, but it had behaviors that made us think it was. It's called Cygnus X1. It's actually, we now know it is a black hole with a massive star orbiting it, and gas is flowing onto this compact object. And the X-ray flux from this object was flickering all the time. So if you look with an X-ray telescope, you see it flickering on and off at very rapid time scales, down to hundreds of milliseconds. And so it's hard, you already realize that you're dealing with a very compact and energetic object when you see this kind of variability. You wouldn't see our sun turning on and off, the whole sun turning on and off on second time scales. It's way too large. So this is telling us that there's the source of the emission is sort of like that time times the speed of light. So, 100 milliseconds times the speed of light. It's a very compact object. That's what made us think it was a black hole. People eventually got to measuring the velocity of this object around it, and by Doppler measurements, were able to see how massive that object was. And it's something like 10 times the mass of our sun, and so it became pretty believed that it was a black hole. There's some nice data that I'll show you here. Black holes can have all different kinds of sizes. You can have ones that are a few times the mass of our sun, 1,000,000 times the mass of our sun in the centers of galaxies, even 1,000,000,000. And the way that we really understand that they're black holes is by looking at objects orbiting them. And if they're orbiting, this really tight, compact mass, we start to think it's a black hole. So we think that there's a black hole at the center of our galaxy. And this is a really nice movie. It's taken decades to have the technology in infrared astronomy to be able to make this movie, because the center of our galaxy is a very cloudy, crowded, obscured area. You have to look in the infrared band to see this. But here are traces of stars all orbiting around this central object. And they come in and they come whipping around. You see, when you trace out all of these different orbits, you can make a measurement of how much mass there is there. And we think it's about 3 million times the mass of our sun. But there's no light coming from that central object. So we think that there's a black hole at the center of our galaxy. And we see with the Hubble Space Telescope that John was talking about, and John enabled it to make these beautiful images, we make images of galaxies outside of our own. And many of them have this compact object at the center that seems to be accreting matter, glowing brightly, sometimes having jets, like this M87 image. Here's the black hole. We don't have the technology yet to image all the way down to the black hole, so I can't show you a picture of one. We hope in 20 years or something with X-ray astronomy we'll be able to really take a picture right around the black hole. So all of the evidence is circumstantial, but I would say every astrophysicist that I know feels very strongly that there must be black holes due to the circumstantial evidence. We talked about Stephen Hawking due to the nice question that came up. Black holes do not radiate. They only, light cannot escape from them. Well, Stephen Hawking proved that wrong. And he came up with this idea for Hawking radiation. And here's how it works. If you have a vacuum in space, you think there's nothing there, but quantum mechanics tells us there's always little fluctuations burbling around. You just can't see them. There's little bits of energy, and then it comes and goes. And these, you can make virtual pairs in the vacuum. So there will be an electron and its antiparticle, a positron, that are created. They come back together. They disappear. You never see them, but they're there. If you have a black hole, Stephen Hawking realized that it has a strong enough gravity to actually pull one of the particles into it. And so, you make this virtual pair, but then the electron disappears, and suddenly you've just got this positron, a real positron flying out. And so a black hole does radiate. We've never tested this because the radiation is so faint. It's very hard to detect. But over the age of the universe, smaller black holes can radiate away, some fraction of their mass. And this is a nice picture, Stephen Hawking getting the Copley medal. And this is Michael Griffin, the administrator from NASA. This was in the 1990s. Martin Rees, a colleague of ours in England, giving him this medal. Stephen Hawking was a real space buff. And he flew on the Vomit Comet once, which was really hard for somebody in his physical condition. This is the airplane that flies in parabolic orbits and gives you weightless time at the top of the orbit. I don't know, do astronauts all get trained on that? Yeah, okay. So, but he flew on it just to experience this. And as I understand it, I haven't done it myself, but John could tell us later, it's a pretty violent experience because it isn't just one arc. It goes 20 or 30 times, and you're weightless, and then a few minutes later, you're slammed down to the ground at 1.8 Gs, and then you're weightless again, and this goes over and over again. So it takes that's why it's called the Vomit Comet, by the way. And there's one other, before I get to Swift, I wanted to tell you one other interesting thing. This curious episode of Walter Wagner. So Walter Wagner is I hope he's not in the audience, but if he is, he can speak up for himself. A dangerous combination of a lawyer and a physicist. And he had this idea that the Large Hadron Collider in Switzerland, on the border of Switzerland and France, when it would turn on, would be able to make energy in these collisions that would be so great that you'd form a black hole. And if you formed a black hole, it could grow and swallow up the Earth. So it was actually, his idea was that it was quite dangerous. And he brought a lawsuit to prevent them from turning on CERN. And he actually brought it in San Francisco, and it was, it was out of jurisdiction, so it was thrown out. And the LHC turned on, and no black holes were formed. Even if there were microscopic black holes formed, they would have such a short lifetime to Hawking radiation that they would disappear right away. So no physicists really believe this. But I read an interesting news interview that he did. And he said, well, I calculate the probability for this is 50-50. And that's a pretty high probability for something catastrophic like that. And they said, well, how did you do that? He said, well, on the one hand, it might happen. And on the other hand, it might not. So 50-50. OK, so now we're going to talk about Swift, my favorite topic, and gamma ray bursts. So first of all, what are gamma rays? I've been talking, even during the questions, we were talking about gamma rays. So I think you already have an idea, and maybe you knew before you came here, that gamma rays are light, just like the light we're seeing with our eyes. But they're very short wavelength light, very high frequency. They're at the shortest wavelength, highest frequency end of the electromagnetic spectrum. At the other end is infrared and then radio waves, which are very long waves. And light has this duality principle that it behaves both like waves and particles. And in the visible band, that you really do you do think about it. You can see the effects of waves. If you see a distant light coming through a screen in your door, you'll see a diffraction pattern. But you can also do photon counting with some cameras where you detect the individual photons of light. In the gamma ray band, we always think of them as particles. They behave much more like individual objects arriving. They're actually packets of waves, but they come as objects that we can count. So we actually count the gamma rays that come into Swift. And you can see here that there's a lot of different satellites. Only the optical band gets down to the ground in radio waves. At very high energies, you can measure gamma rays because of their effect in the atmosphere. Most of the electromagnetic spectrum, you have to be above the Earth's atmosphere to study. And so astronomy and astrophysics has gone through a revolution in our understanding of the universe as we've been able to launch these satellites above the Earth's atmosphere and make these measurements. Satellites like HST, Chandra in the X-ray band, Spitzer. And in the gamma ray band, we have Swift, and we also have a mission that John mentioned called Fermi that's flying right now. So that's what gamma rays are. And then what are gamma ray bursts? Gamma ray bursts are flashes of gamma rays, really bright flashes. They dominate everything else in the sky when they occur, and they last very short time. They only last like 100 seconds. So we don't have anything similar in the optical band that we see, where you look up in the sky and you just see a star come for 10 seconds and disappear. The closest thing I can think of are these glints off of satellites. They'll sometimes make a bright flash. I don't know if you've ever seen any of those, but they are visible to the human eye. We're not very familiar with that kind of transient sky like we have in the gamma ray band. They occur about once a day. With Swift, we see one every few days. We don't see the whole sky. And they were discovered by the Vela satellites that were built at Los Alamos. So John F. Kennedy signed a test ban treaty with the Soviets in 1962. He actually signed it just the year before he died. And it was to prohibit testing of nuclear weapons above the Earth's atmosphere. And Los Alamos was tasked with building these Vela satellites. They were launched in pairs. You can see two of them here. And they had gamma ray detectors on them. Gamma ray bursts make gamma ray flashes. Well, so do bombs when they go off. In fact, it's the gamma rays from a bomb, the X-rays and the gamma rays that are the most fatal part of it. Like in Hiroshima and Nagasaki, people got radiation damage mostly from X-rays and gamma rays. So they had gamma ray detectors on the satellites, and they started detecting flashes of gamma rays, which, lucky for all of us, it was not nuclear weapons testing. They discovered gamma ray bursts. This is what a gamma ray burst looks like to an astrophysicist. It's the counting rate in the detector that suddenly goes up. It's counting 1,000 counts per second of these individual gamma rays coming in, and then it dies away. This one lasted for 6 seconds. It's the first gamma ray burst that they saw. And since they were so bright, it occurred fairly often, everybody, even when we were students, were thinking that these must be coming from somewhere nearby our own solar system or somewhere within our galaxy just because they were so bright. And that was thrown out of the window by discoveries in the late 1990s, both with the Compton Gamma Ray Observatory, the BATSI instrument that John mentioned, and also by an Italian-Dutch satellite. They were able to position a gamma ray burst very accurately on the sky and then follow it up. This is a little bit later in time, but it's the nicest image I have that shows you with the Hubble Space Telescope. Here's the gamma ray burst. It was detected, it's dying away, and here it is in a distant galaxy. It's not nearby our solar system, it's not even in our own Milky Way. These gamma ray bursts are coming from far out in the universe. And so if you put that together, they're bright, they're really far away, you realize that they're a huge amount of energy. So they're the most energetic explosions in the universe, people say, after the Big Bang. They're about 10 times as much energy as a normal supernova. And they're really fascinating objects. My friend at Los Alamos, Ed Fenimore, put it in this way, which is maybe one way you can sort of appreciate the energy. A nuclear bomb, which has a huge amount of energy, tons of TNT, is equivalent to just taking a raisin of mass and converting it into E equals mc squared of energy. So, mass converts into a lot of energy without much. But a gamma ray burst is the equivalent of taking 400,000 Earths and having them, that much mass just suddenly vaporize, E equals mc squared. So there's really a huge amount of energy in these gamma ray bursts. Well, that's what motivated us to propose the SWIFT mission, because this was the late 1990s, and we realized that these were really neat. We don't understand what they are. They're important in understanding the universe because they're so bright. They have a lot of effects that I'll show you. And we can use them as tools to study the early universe because they're these bright beacons that come from far away. And so we can use them to study the distant universe in a way you can't do with other techniques. But they were poorly understood. We didn't have any really good set of observations. And so we needed, first of all, a good gamma ray detector. And I'll show you about that. And we needed a rapidly responding spacecraft. And that's why this whole mission is called SWIFT, because we proposed a mission. It's an astronomical robot, and it can control itself and point at the gamma ray burst. What we had, and I think this is one of the reasons we were able to win this big competition in '98, was this new technology. We didn't invent it at Goddard. It was invented by the medical imaging community. And it's this solid-state detectors called CAD-zinc TEL detectors. This is the size of them. They're very small, but they're solid-state. They can run at room temperature. They have a lot of advantages over other things like silicon detectors. And we found a way to build very large arrays of this. So on SWIFT, we have 32,000 of these detectors. And I brought one of the modules. This is 128 of them that you can come down and see afterwards. This is actually a flight module. So we fly, this has 128 detectors, and we have 256 of these modules in our array. So it's, it's about this size. It's the size of a coffee table, all with these precision solid-state detectors. It's by far the most sensitive gamma ray camera that's ever been built. This is what SWIFT looks like. This is the instrument that's this gamma ray camera with all of those CAD-zinc TEL detectors in it. It views the sky through this thing called a coated mask, which is a big mask with lead elements on it. It allows us to do imaging in the gamma rays. And then we have an optical telescope called UVOT, UV optical, and an X-ray telescope. So the way the satellite works is this wide field gamma ray instrument is looking up at the sky. It doesn't matter where it's looking. It's waiting, waiting. Then a gamma ray burst goes off. And we're able on the fly with the high power computer that we have on board to calculate where the position was. We tell the spacecraft, and it autonomously slews to point the UVOT and the XRT at it. And we can look and see the dying away X-ray and optical emission after this flash of gamma rays. That's how SWIFT works. And it also sends the data right down to the ground immediately through a relay satellite called TDRS that NASA runs. And so astronomers on the ground can point their telescopes at the gamma ray burst. And they do. Whenever we have a gamma ray burst twice a day, and every time, I mean twice a week, sorry. We wish it was twice a day. And every time we have one, there's people scrambling to make observations. You have to observe. This X-ray and optical afterglow lasts only for about a day. You have to observe quickly, but when you observe, it can be very bright. It's nice to have this advertisement from these Swift trucks that you may see rumbling around the Beltway, although that can have its downsides sometimes. We put this satellite together. It was the busiest time of my life, building this satellite with this team of about 100 scientists and 100 engineers and managers that we had. But it was a wonderful time because you could see it come together in the clean rooms at Goddard. We bought this spacecraft bus, they call it. It's basically the structures and the solar arrays from a company in Arizona. It's now owned by Orbital, but it was called General Dynamics at the time. And then we built these telescopes. We got parts from our European partners in the UK and Italy, and then we assembled them here in the US, and we built the large gamma ray BAT instrument right at Goddard. And here it is all put together still at Goddard. That's me pointing where we want to go. And so then we shipped it down to Kennedy Space Center. And that was a fascinating time. I've been to other launches, but this is the first time, it was sort of our own satellite that we were launching. And we launched on a Delta rocket, Delta II rocket. Here's the solid rocket booster. So this is full. Basically, it has 10,000 gallons of kerosene and 10,000 gallons of liquid oxygen. And it's a solid rocket, so you can turn on and off the rocket and steer the nozzle. That's what's nice about a solid, the liquid rocket. It's surrounded by these 3 solid rocket boosters. And these have a tremendous amount of energy. They're solid explosive, essentially. They're solid nitroglycerin. But what's good about them is you get a huge amount of power. What's bad about them is when you light them, you can't turn them off or steer them. So when you light them, they're like firecrackers and you're going. And here was our precious satellite. It wasn't my life on the line, but I felt like it was, John. This is this satellite, this instrument that we've been building for 7 years, and it was on top of this bomb. There's a nice picture of it. When we went down to Florida in 2004, it happened that this was the most hurricane active time, and all these hurricanes happened after we shipped. So we were sitting down there at Kennedy Space Center. This was where we launched from Cape Canaveral. And some of them, tore the siding off of the vehicle assembly building. They were violent hurricanes. And so we had to hunker down in our hotel room. We actually had to put Swift back in its shipping container to protect it. And all we could think of is, we want to launch. So we had this idea, we launched right through the eye of the hurricane. Why not? Because it's calm, right? Have to push the button at the right time. Well, finally, the double rainbow came out, and we knew it was good omen, and that's when we launched. So I'm now going to show this video. I think it's still on mute. Okay. So this is a picture of the launch, a movie of the launch of Swift. And it's a really nice movie because in addition to the cameras on the ground, they had a real telescope, a Questar set up. And so you'll see the rocket go up, and you'll be able to see the solid rocket boosters fly off of it. It was a beautiful, clear day.
15, 15, 10, 9, 10, 8, 9, 7, 6, 5, 4, 3, 2, 1, 2, we have ignition, we have liftoff, and we have liftoff of NASA Swift on a mission to study and understand gamma ray bursts throughout the
I told him
universe.
to say that.
Everything continues to look good.
I'm going to turn it on mute now so I can talk over it. So we're going to see the rocket go through the sound barrier. At that time, if you're able to see it well enough, you'll see a cloud of vapor form around the nose cone. That's coming up soon here. Look there. Okay, there we are going through the sound barrier. And here's with this Questar telescope, and you see the solids flying off. It was kind of an interesting experience because that was the shroud coming off. We launched on a Delta II, which was managed by Boeing. It was a Boeing rocket. And after we launched and got on orbit, all the Boeing guys stood up and started shaking each other's hands, and we're all clapping, and everyone was happy. But you know, for us, the rocket was very reliable. We weren't that stressed about the ride. We were more stressed about all of our own deployables coming out and the telescope turning on. And those guys just walked out of the room and left us with our telescope. Luckily, everything worked well. And this is some beautiful pictures we have from the UV optical telescope and the X-ray telescope of different galaxies. We don't spend all of our time looking at gamma ray bursts, although I'll be showing you those data. And when we're not looking at gamma ray bursts, we're looking at objects that people in the community ask us to look at. And so we get requests, and we schedule about 7 different observations a day. And everywhere you point Swift, you get a multi-wavelength view of the sky. You can see in the optical, you can see in the UV, and you can see in the X-ray. Look how different galaxies look in these different bands. In the optical, you see the whole galaxy. In the ultraviolet, which are the middle panels, you see the star formation regions in the galaxy. These are all spirals. And then in the X-ray band, you don't see that at all. You tend to see neutron stars and black holes and compact objects that are making high energy emission. This is what the gamma ray burst data look like. So when we get the burst detected by the BAD instrument, there it is on the sky. We position it right away, get this position to a small fraction of a degree. Then almost every one of them has an X-ray afterglow. And so there's the X-ray source. And this X-ray telescope is really nice because it can position them really precisely to arc-second precision. So about a factor of 100 better than the BAD instrument. And then we take a picture of the whole sky with this optical telescope. It's not as big a telescope as the HST, but it's very capable, and we can point it all over the sky. So we do a lot of different optical astronomy observations with the UVOT. And this is what a gamma ray burst looks like, as I mentioned earlier, to a gamma ray astronomer. It's this counting rate versus time. Now look at this one. This one lasted 30 seconds. You know, it turns on, it turns off. It sort of looks like Cygnus X1, but much brighter. It's very erratic. Well, here's another one, a very short one. This whole thing lasted only a second, and yet it still has these really high time fluctuations. And although we don't really understand what causes all these fluctuations, I'll give you some speculation in a few minutes what we've learned with Swift. And here it is. This is heaven to my eyes. It looks like a bunch of squiggly lines to you, but here's a whole page of gamma ray bursts and all of their light curves. And this is just a fraction. We now have 700 of them that we've detected and performed these detailed observations on. So let's see what we're learning from this. First of all, I mentioned that you see a gamma ray flash that lasts for a minute or so, or tens of seconds. And then afterwards, there's this afterglow in the X-ray and gamma rays. And here you see the X-rays fading away. This is over about 1,000 seconds. So here's an hour. It's very bright for a while, and then it kind of flatter and decays away. One of the things that we've learned is that the gamma ray burst actually lasts much longer. It's just that we never had an X-ray telescope that could look that quickly. And so the real show is still going on for hundreds of seconds. And then in the optical, we've looked with HST, which has the prettiest images, but we look with a lot of other telescopes too. And there's something really important about this afterglow that we see in the optical band. It's extremely bright. It can be 1 billion times, 1 million times to 1 billion times brighter than the galaxy it's in. And so we're getting a lot of light from this distant galaxy in the universe. You have to be able to observe it quickly, But if you can use it to study that galaxy in a way that you can't in any other way. Because these distant galaxies are so faint you can't see them even until the gamma ray burst lights them up. Now this is the record holder that we had. And this is actually the most distant object that's known in the universe with a so-called spectroscopic redshift, a very accurate measurement of its distance. And it occurred 13 billion years ago. So the universe is 13.7 billion years old. This occurred from one of the early stars that were formed in the universe, in early galaxies. And the light has been traveling to us remarkably for 13 billion years. And when we were talking at dinner tonight beforehand, a lot of different objects have exploded and their waves of light are heading toward us. We don't even know what's on the way, but it's all been launched. It was, especially with these gamma ray bursts, they were launched a long time ago. And we're just sitting here waiting for them to hit the Earth and for us to study them. This is a beautiful picture of how bright that is, even at such a great distance. What you can do with these is a lot of great science. I'm not going to go into the details, but I wanted to show you this one beautiful plot. This is a spectrum that's taken of one of these gamma ray bursts. It's a very far away object, and it's in the optical band. And this one is taken with the Keck telescope on Mauna Kea in Hawaii. It's a huge optical telescope. What we're looking at is how much light is coming from the gamma ray burst as a function of the wavelength. So this is very red light. This is more into the visible light. And what I want you to see are all of these absorption lines. So as the gamma ray burst shines through the gas of its galaxy, it's absorbed by different elements in the galaxy. You can see iron, magnesium, silicon, nitrogen. And we can see by which lines are there how much nitrogen there was, how much there is, how much carbon there is. And so we can measure the elemental abundances of this object that's at the very early part of the universe. And that's one of the great tools of gamma ray bursts, is to study the early universe and try to see how the elements were formed, when they were formed, when the first stars occurred. It's kind of a nice, maybe a nicer picture to look at this. So here's the history of the universe all in one panel. So first of all, there's the Big Bang. It's shown as this glowing white light. And then eventually it cooled down and the whole universe became, there were no stars or galaxies yet, and all the electrons found protons and became hydrogen atoms, and it became neutral. And they call this the Dark Ages because any star that formed, its light would travel through the medium and it would get absorbed, and you wouldn't see the star even because the light couldn't travel very far. But then stars started forming in galaxies, and trying to understand when that happened and how it happened is one of the major problems in astrophysics right now. And they emitted light that reionized the universe and made it transparent to the way we see it now. So we can see across the universe, and you can see stars and galaxies. And you can see here, these are redshifts. These are the millions of years ago. The gamma ray bursts are probing back into these very early times that we can't see with other satellites. It'll be neat when JWST, this future satellite beyond the Hubble Space Telescope, is on orbit, because it's also going to probe back into this very early time in the universe. And we hope SWIFT is still up at that time, knock on wood, or at least that we have some way of detecting gamma ray bursts when JWST is there. Now, one more result I wanted to show you, and that is on the opposite end. And this is the very nearest gamma ray burst that we detected. They have names. This is 2006, February 18th. That's the date that we detected this one. And it's probably our most famous gamma ray burst. In fact, I did an interview with Science Magazine yesterday about this burst that occurred 6 years ago. And what's so special about it is that it lasted a long time. This one actually lasted 35 minutes. And when a gamma ray burst goes off, the signal comes to the ground and goes to the telescopes, but it also comes to our cell phones, and so we get paged, and we go running to our computers. And I still remember this was at 2 a.m., and try to figure out, what is this object? It's lasting 35 minutes. It doesn't seem like a gamma ray burst. It had a very smooth curve. It wasn't jaggedy like the other ones. And then we had an aha moment around 4 a.m. when we said, oh, it's just a really long gamma ray burst. It must be nearby or something strange. So we sent out astronomical telegrams to the whole world saying, look at this with your telescope. There's a really odd object in the sky. And so everybody was observing this. And the next day, a supernova started to occur in that part of the sky. And so this was a tie-in between these gamma ray bursts that we were seeing and exploding stars. And it wasn't just any old supernova. It was a very high velocity. A supernova is a star that explodes. People have seen them historically. We haven't had a nearby one in the sky. When they go off, they can be so bright that everybody will see them. It'll be as bright as Venus. Hopefully sometime in your lifetime you'll be able to see a supernova in our galaxy. But there's a tie between these gamma ray bursts and supernovae. I'll show you a little movie in a minute. And they're very high velocity. We call them hypernova. And you can see here, this is an image. It doesn't look very bright, but it's still at a pretty good distance. It's 450 million light years away. It's much brighter than its galaxy, and it's shining there. This is a nearby supernova, and you can see how they occur in galaxies. We see them in external ones. They appear for a while, they last for about a month, and then they disappear. Okay, so that gave us the tie between gamma ray bursts and exploding stars. So now this is what we learned. So this is what happens to a star. I showed you this onion structure of a star. The core burns to iron, and it collapses. There's no more radiation there. Gravitational weight of the star pushes down, it collapses. And in a normal star, a massive star, this core collapses to what's called a neutron star. It's a hard core of a star, but it's not a black hole. It has about a 10-kilometer diameter, sort of the size of our beltway, but it's a lot of mass within that small region, but it's a neutron star. And then the rest of the star goes shooting off, making this bright explosion we call the supernova. And here's what we strongly believe now happens in a gamma ray burst. It's a more massive star. The pressure is larger in the center, and so it presses all the way down beyond this limit that Schwarzschild found and that Oppenheimer found. And so this neutron star collapses down to form a black hole. And when you form a black hole at the center of a star, a lot of things happen. First of all the mass starts falling into it. It's a really strong gravitational pull. It forms this disk. It makes jets that beat their way out through the star. And these jets are aimed at us and make the gamma ray burst. And then it also explodes the star in this very high velocity hypernova. So here's the video. So we're going to ride on a camera into the center of this star. We're going to see the black hole form, and we'll see the jets come shooting out. I hope it plays. Looks like it's good. So there we are in the center. There's the iron core, collapses to a neutron star, and then all the way to a black hole. It actually should be just a point. Gas is flowing down onto this black hole. Jets are shooting out. They have such high velocity, they burst their way out of the star. And these jets are what are making the gamma ray emission and the gamma ray burst. And so one thing you'll learn from this movie, if you looked at it, is that we see a gamma ray burst when that jet is coming at us. And there's a lot of these exploding stars aimed somewhere else. Some other civilization may be seeing them, but we don't. We only see about 1 in 1,000 of them. We can learn a lot of things. I have 2 view graphs to show you just the kind of things we can learn about black holes from gamma ray bursts. So counting the GRBs gives us an estimate of how many black holes there are in the universe. We know of a few dozen from these velocity measurements, but that's so few. When we take the current GRB rate observed by Swift and assume that that's been going on for like 10 billion years of the universe, you come up with about 1 million black holes in every galaxy. People think there may be between 1 million or 10 or even 100 million. They have no idea, but these gamma ray bursts are telling us the number. And then sort of bringing it closer to home, gamma ray burst extinctions gets everyone worried. Well, you don't have to worry, but there's real science here. Actually, we've done this at Goddard where people study the ozone hole. They've developed computer codes to understand how ionizing radiation hitting the atmosphere can affect it and can affect ozone for solar flares. If you have a gamma ray burst that's near a planet with an atmosphere, It can destroy the ozone layer. If it's close enough, it can blast the atmosphere right off the planet. The GRB must be really close. It has to be within 1,000 light years. That sounds like a big distance, but there aren't that many stars within that distance. And so we worked out the probabilities, and we think that this kind of gamma ray burst blowing the atmosphere off the Earth, or at least destroying the ozone layer, probably has happened a couple of times during the time that there's been life on Earth, since the Paleozoic era, causing some extinctions. This is a new field. It may be one of the causes of extinctions. But the probability that it happens, in your lifetime is minuscule, much less than an asteroid hitting the Earth. So you don't have to worry about one of these. But another way of looking at it, though, is every time, every 2 times a week when we detect a gamma ray burst, some poor planet nearby got completely vaporized. So it is happening. Okay, so now I'm going to close. I wanted just to discuss a few of these sort of mind-boggling things about what really is a black hole. Well, of course, it's an object that's just full of unmatched socks. We all know that. There are actually a lot of different ideas of what, in physics, is a black hole. I talked about general relativity. In that case, the black hole is just a point of mass. The whole star is collapsed to a mathematical point, a singularity. And I gave one of these lectures kind of similar to this one for a different audience, and somebody in the audience said, wait a second, a black hole can't be a singularity. There's only one singularity. That's what the word means. So I don't know. It's a mathematical term that means everything is concentrated at a point. We call it a singularity. That's the general relativity view of a black hole. And then there's a Schwarzschild radius around it, and light can't get out from it. Then there's also the idea that it's not just complete, what's it like inside the black hole? Well, it's not just completely black because there's radiation that's coming, there's matter that's falling into the event horizon of the black hole and falling in. And so it's radiating. It would be lit up inside with a lot of things falling by you all the time, sort of a really violent place. Now, each of these actually, these are not just sort of ideas somebody had, but these are real papers that people have written. So these are serious ideas. So this is another one. All the mass is accumulated at the event horizon. There actually isn't anything inside. Okay, here's a way of looking at that. And this comes about because if you watch matter falling into a black hole, you'll see that it gets time dilated, which means the time slows down more and more as this matter gets closer and closer to the black hole. And when it gets to the event horizon, from our external point of view, time has stopped. And so, wow, maybe nothing ever actually goes through the event horizon. It's just all piled up there. Well, there are good arguments why that probably isn't the case. If you have a star that collapses to a black hole, there already was mass inside there, so there must be something inside. And also looking at it in a proper quantum mechanical calculation, well, actually it's proper calculation taking into account general relativity, an observer, or some of this mass that's falling in the frame of that object does go through the event horizon and eventually does plunge through. Okay, this is one of my favorites, I think, and that's that we don't have a theory of everything that we were discussing in the questions before the talk. So maybe there must be quantum mechanics that comes in when you have such a tight gravitational field, such a strong field, that it's not going to be a point. It's going to be some kind of quantum fuzzy ball in the center. And other people have said that the whole black hole is sort of filled with quantum fuzz. These last two, I think, are kind of fascinating. One is that black holes are portholes to a parallel universe, and the other is that every black hole forms a new universe. So let's talk about that for a minute. So you can have these things called wormholes. We don't believe there really are any, but mathematically you can have them, where you can transfer between one point of the universe to another through a black hole. So the idea is that these black holes, whenever one forms, it's essentially giving you a path to a different place in the universe. The trouble with that theory is that there's no way to ever test it. This other one is pretty fascinating too, and that is every time a black hole forms, there's a new universe. The whole universe is within that black hole. You can think of our universe as being a black hole. And then there's the idea of cosmic evolution. So the universe develops in such a way to make black holes. Ah, that's interesting. We live in this universe where really bizarre things happen. You know, these massive stars evolve and collapse into black holes. You know, who could have ever thought of that? Well, these preposterous things are happening because they make black holes. And we're in a part of the universe where black holes are being formed because there's a kind of natural evolution towards the creation of black holes. So think about that for a while. So now, what would it be like to fall into a black hole? So I talked about clocks moving slower and slower from an external observer. But if you're actually traveling into the black hole, in your frame, you don't see that. You see the rest of the universe become more and more redshifted and their clocks slowing down, but your clocks are going just fine and you can plunge right through. But if you look at the Schwarzschild equation, what happens when you go through this singularity is that the coefficient in front of the time term and in front of the space term change signs. And so you actually get a swap between space and time inside the black hole. This is the mathematical structure that you come out with the Schwarzschild equations. And so we're used to, in our world, time is inexorably moving on, but you can move around in space from one place to another. Well, inside a black hole, space is inexorably moving along, and you can't change your space path, but you can move around in time. So that's another kind of bizarre idea. Okay, there is something kind of fun that happens, or bad that happens if you're the person, this thing called spaghettification. And so what happens is that if you're a person falling into a black hole, you get close to the black hole, and the gravitational field at your feet, the gravitational pull at your feet is so much stronger than it is at your head that it stretches you out. And so this happens actually, we believe, to all matter falling into a black hole. And for a very small black hole with just a few times the mass of our sun, there's a really big gradient, and it would just tear any astronaut falling into the black hole. But if you had a massive black hole at the center of a galaxy, it would be a more gentle ride, and you'd be able to plunge right through. I like to collect pictures, and these are ideas, sort of what people think about black holes. This is a gamma ray burst with this guy shooting out along the jet. Here you see the black hole at the center with these jets. This is a star falling into to become a black hole. And this is also more of a sort of gamma ray burst kind of picture. And you can see with time that the way people have viewed black holes has changed. This is a 70s artist impression of a black hole. It looks kind of like the Wizard of Oz, I would say. You know, kind of everything, you can see the cows in the barn falling into the black hole. But here we are nowadays, you know, anime, of course. And so this is what it looks like nowadays, falling into a black hole. I have my conclusions, and I have one more slide after that. So objects exist that look and behave like black holes that were predicted by general relativity. We haven't been able to image one directly. I hope, you know, hopefully in my lifetime we'll be able to do that. But we have a lot of indirect evidence, and it all points in the same direction that there really are black holes. They're common in the universe. We know by name a few hundred, but we can tell by extrapolating out in space that there are, you know, millions in our own galaxy and billions in the universe. But we still don't know really what the true nature is of these black hole monsters. So with SWIFT, we're observing the fiery birth of black holes. We have these GRBs that are a new tool for studying the universe. And we very much, with SWIFT, hope that we can detect one of these gamma ray bursts from an even more distant object, hopefully from the very first generation of stars in the universe. This is a meeting that we had recently, and I just wanted to sort of publicly thank this team that's working on SWIFT. We have 200 team members all around the world. About 100 of them are in the US. And then we also have about 5 times that many users of the observatory that are just out there in the astronomical community that put in requests. And it's a great lot of fun working with this satellite, and we hope that it stays in orbit for quite a ways still. Thank you.
trying to grab the
There you go.
Yeah, thanks. Well, thank you very much. Am I on? No, I'm not on. Now, am I on? Hello. Okay, we have some time for Q&A. I imagine there might be a question or two right here in the middle.
This might be a bit off topic, but I remember hearing something about gamma ray bursts being associated with magnetars and blazars.
The question is, are gamma ray bursts associated with magnetars and blazars? Oh boy.
This is a topic that may be closer to John's expertise, but indeed, these very magnetized neutron stars, that's what a magnetar is, do make flashes of gamma rays. And in the early days, there was a really bright flash of gamma rays in 1979 that I remember. In fact, everybody in the community knew about it. We thought it was a regular gamma ray burst. It turned out to be one of these magnetars that was in a nearby galaxy. And so they're different. The physics is different. The observations look very similar.
Way in the back. Okay, the question is, what is the youngest black hole that you know of?
Well, every time we observe a gamma ray burst, there's a brand new one forming. So, those are really young. Okay, yeah, I understand. I understand what you're saying.
You're talking about light travel time. So the youngest in terms of this time frame. Oh boy.
There's no way to really measure their age very accurately. These very massive stars don't live very long. They only live about 1 million years before they collapse and make neutron stars and black holes. But then they sit there and they can either be dark if there's nothing around them, or if there's some other star around them, they'll be accreting matter. And so we don't know their age. We can tell how long they've been lit up sometimes by sort of the age of the star that's around them.
Okay, question here.
On all your plots, the graphs showed 2 peaks. Do we know why there are 2 peaks instead of 3 or 4, or 1 peak, or like the reason for that?
Okay, on all the plots that he showed seem to have 2 peaks. And the question is why, or what does it mean? Yeah.
Well, that was just a selection effect of my picking some to show you. There are a good number that have 2 peaks. This one has maybe 3 or 4 or 5. And there are also ones, now of course you won't be able to see this very well, but there's some that just have a single spike. And so if you can maybe scan your eyes over this, you'll realize that there are some really interesting ones with 2 peaks, but they don't seem to be a separate population that we know of.
Over here at the far right, yes.
Just wondering the difference between most of them that you said lasted a few seconds and the one that was 35 minutes.
Oh, yeah.
Are they all creating or the results of supernovas or hypernovas, or do we just have a really good angle on that one?
So the question is, is there one family of events causing this, one particular mechanism, or is it different mechanisms causing much longer bursts than shorter bursts?
It's one of the main questions we wanted to answer with SWIFT. And bursts that are longer than about 2 seconds seem to be all the same. These ones that are really long, that last many minutes, we think maybe the jet is just barely getting out of the star, and so it's taking longer. So the basic idea is the same, but it's but it's a little bit different in its tuning. But then, what about less than 2 seconds? So I haven't gotten into that, but we think there's a different complete mechanism for making bursts that are less than 2 seconds. And it's the results that have come out of SWIFT. And those are actually probably due to neutron stars that are orbiting each other and then merge in a fiery collision, also making a jet. It's fairly preliminary data, but it's a very interesting question that you ask. We actually believe that there's 2 different ways of making gamma ray bursts. And I'm glad you asked, because I didn't have time to get into that.
Okay. Question right above him. Yeah.
We know NASA's tracking near-Earth objects, asteroids, and so on for dangers. I'm curious as to, you mentioned the unlikely but possible idea of getting gamma ray out of existence by something within 1,000 light years. Is there any tracking of potential objects or anything like that?
I didn't hear the question.
Oh, I'll
I'm
repeat
sorry.
the question.
Yeah, thanks.
He was asking, are we tracking any objects that might become gamma ray bursts near enough to harm the Earth? And actually, we have been doing some studies to see where there are really massive stars that could explode that are in the neighborhood. This isn't really to predict one because, you know, there's still thousands of light years away. And there is a very massive explosive object called Eta Carina, which is, we talked about during dinner, which had some explosions in the past. And when it goes, it's a 100 solar mass star. It's going to make this huge explosion, and it's just a few thousand light years away. So people have gotten interested in this topic. It's a good question. We're not tracking them in the way that we do asteroids, though.
There was right here, yes. And then we have time for one or two more, but that's it. And we don't know if it's clear outside, but if it is, if you can see Mars, if you can see Saturn, just two bright spots in the sky, our telescope is open for your pleasure. Yes?
In your talk, you mentioned the rate of seeing these being per week, but you've not mentioned anything about a distribution. Are you seeing any part of the sky where these are generating more so than any other part?
Yeah, the question is there any distribution pattern over the sky, or do they appear everywhere in the sky?
They appear uniformly in the sky. The BATSI instrument that was on the Compton Observatory that we talked about at the beginning and John mentioned was the first instrument to measure a large population of gamma ray bursts and to see what their distribution was on the sky. They were looking to see if there would be a concentration along the Milky Way plane, just to determine the origin. And it's very uniform. Everything's statistical. We went 3 months once without seeing one, and we've gone other days, you know, there were days where we had 4 in a day. But on the average, it's 2 a week. And if you look at the distribution, it's just like rolling the dice, you know, it's just statistical. So it seems to be a uniform rate and time and uniform on the sky.
I just want to add that that is exactly the same logic that William Herschel used for the distribution of nebulae, realizing that they'd had no concentration toward the Milky Way or the galaxy, and he started making him think in the 1780s that there's something else out there, and that's what we're faced with here.
And they were the galaxies, right?
And they were the galaxies. That's right. Back in the red there. Could you talk about supernova 1987A?
So that was the nearest, as you know, the nearest supernova that we've had in our lifetimes. And it did not make a gamma ray burst, we're pretty sure. It was a kind of a very interesting supernova because of its proximity to Earth. And we've been observing it with HST and Chandra, seeing rings come out of it. And I actually did, in my postdoc, we flew a balloon instrument, a high-altitude balloon instrument in Australia to observe gamma rays from supernova 1987A. So it's one of my favorite topics.
Quite a supernova event. Okay, one more question, then we will, those of you who wish to see the detector, you can come on down here after that and maybe ask a few more questions. Yes?
Can you explain why the jets are emitted and what causes the velocity of the jets? Is it a magnetic field or is it light pressure from the disk?
What causes the jets? What's the mechanism that causes the jets and gives them their high velocity?
Yeah, that's a hot topic right now. And we see jets in many different kinds of sources. You know, we see them not just in gamma ray bursts, but also from the centers of galaxies. I had this one image here. And it probably is magnetic fields, actually. So you have a black hole at the center, possibly even with a neutron star, but let's talk about a black hole. Masses orbiting it and accreting onto it, and there's magnetic field in this disk that gets twisted up by this rotational motion, and it can make a kind of funnel that'll collimate the particles that come streaming out. So that's our best guess right now what makes these jets. I've often thought, I've given lectures on the topic that, you know, whenever there's a black hole that's accreting matter, you have some kind of jet coming out of it. They seem to be very common. And they may be a signature of black holes.
Are the jets charged or neutral?
Are the particles charged or neutral?
We think that there's charged particles coming out. you know, electrons and some people even talk about protons coming out. There are other models where people have mostly photons making the pressure, so mostly light that's created in there. So it's an open question right now exactly what's streaming out. The gamma ray burst comes from the streaming out particles that radiate gamma rays at us, for those of you who are interested in the microphysics.
Well, on that, and especially, it's lovely to end on an open question, don't you think? I want to thank all of you for a great set of questions, and certainly give another round of applause for our speaker.
Thank you.
And once again, thank our sponsors, NASA and Aerojet. I want to invite you back for the final session. That will be on June 5th. Where Dave Latham from Smithsonian Astrophysical Observatory will be talking about the Kepler mission. And of course, that is very nicely timed with the last transit of Venus across the face of the sun that any of us will probably see in our lifetimes. And you're all welcome to come. Thank you very much.